everybody. I'm Davide Calzolari. Welcome to the 5 hours presentation session everybody was looking forward to. I'm a PhD student at the Technical University of Munich, working at the DLR. My talk is about the methodology to exploit model oscillation for locomotion of springy robots. So the inspiration behind my research is comes from how animals and humans are so efficient and robust at generating periodic motion. The storage and release of energy in very soft elements like tendons and muscle plays a relevant role in locomotion, and this is particularly important for dynamic activities like running. So also robot can achieve a wide range of very efficient cyclic motion if we equip them with soft springs. And we hope that in this way they can achieve biological performance. On top of that, we know that they're also so easy to control. No? So one way to generate and control efficient oscillation for locomotion is to look at the theory of nonlinear modal oscillation, which is essentially we can inductively think it as an extension of the concept of linear modes to the nonlinear case. And we would like to apply these theories directly to locomotion, but unfortunately they are not mature enough for this, so my research is an attempt to bridge this gap. Alright, so the main idea is that the gate arises from the oscillation itself. So we start from a very simple model of an inverted pendulum equipped with a soft spring, a radial one and a torsional one, possibly non-linear. We attach the foot rigidly to the ground so that we can calculate its non-linear modes. So since the system has 2 degrees of freedom, in a sense, we know that there are at least 2 modes. The amplitude increases with the energy of the oscillation, and the first one on the top is a bit boring, it's just jumping in place, but the second one is more interesting, and I have used it for forward hopping. So from the theory we know that there are surfaces called eigenmanifolds which collect families of the curve that correspond to the oscillation, and each energy level on the surfaces identifies autonomous solution of the system. So now the idea is, how do we use this information to generate gates? What I did, I connected the various stance phases, so I connected the modes using knowledge of the surface and intersecting it with the visible part of the stance phase, which is induced by the fact that we have the unilateral ground constraint. So if you do that, you get a mapping between the attack configuration and the energy, and you can use it to be sure that for every energy level you always come back to the same, to your natural oscillation, and you remain on the mode. And lastly, we add a controller to sustain the oscillation. There is a stabilization part and an energy regulation part. So we have tested this on a 2 degrees of freedom lightweight leg, which basically realizes the model that you've just seen. This is equipped with 2 serial elastic actuators. Here you can appreciate the natural responses of the spring. The motors are locked, so it's off. So the simulations show that robust and highly regular motion was possible, and also that the energy was only injected to sustain the oscillation. So I tried to extend this idea to a more complex system, such as a sagittal quadruped. And here I start from a reduced model, which helps me to design the springs and the mode at the same time in order to find useful motion. So since the system constrained to the ground has 3 degrees of freedom, we know there are at least 3 modes. And the first 2, they could be used for something, I don't know, but the last one is very interesting because we can use it as a primitive for throttling or prompting. So again, I have applied the same methodology, and I have performed a simulation of the full quadruped model which accounts for losses, impacts, and realistic masses. And here I perform plotting at two different energy levels by regulating the energy, since the energy is related to the speed of the gate. And I also perform crumping in the same way, and it seems that the system can withstand the perturbation and the mismatch between the mode and the actual system. Right. Okay. So I would like to conclude with an outlook. So the philosophy behind this design is that we want the gate to be driven by oscillation. We don't want the robot to track a particular trajectory. We just care about excited oscillation. This is performed using a relatively simple controller, and no compensations were required. This gate seems intrinsically robust to perturbation, and this is because we are close to the main mode of the system. So I'm looking forward to the next steps. The most straightforward one being considering lag mass and inertia in the model applied to the 3D case. There is also the idea to combine multiple nonlinear modes and switch them at the right time. And finally, also it will be important to study theoretically the stability of these orbits. Thank you very much.
3 minutes for questions. Please.
So, thanks for that great talk. I saw that in your slip model, you added the spring to the ankle, or maybe fixed the hip and add the spring there. Would it still work without that spring if sort of your equilibrium is not stable anymore?
Yes. Thanks for the great question. Yeah, so this is something I was struggling with for a long time, because in order to generate nonlinear mode, until now we need a stable upright equilibrium, right? And if you remove the spring, you don't have equilibrium. It's going to be unstable. And I have seen that, I think that locomotion is inherently unstable. So this design actually generates some gates that are like one part of the story, how you can locomote. But I think that there is a difference to biological systems because of that limitation. But still, yeah.
You finish your sentence.
Yes, thanks. But still, actually, this mechanism increases the robustness of the oscillation.
How is the following thing different from what you did? Take a robot and you think it's more efficient if you put springs on it, so it looks like a nice design and can do things, and then do some kind of optimization with that design and whatever power supply you have. So do trajectory optimization or policy optimization or whatever, and you will discover in that process your nearly passive gates. Why is that? Why do you have to grow it out of the passive gates rather than just discover the passive gates by energy optimization and say?
Sure, great question. Of course you can do it, and actually I'm also doing it in parallel to check. But the point here is that you skip that optimization of the whole gate, and you just look at the oscillation of the system during stance. And I noticed this is much simpler than having to find a passive gate, because you just look at the oscillation of the system. You don't even have to, have to interact with the grounded pole. It's just an intrinsic property of the system. And this helps with this philosophy that we just excited and see what happens. And also, the point is that if you have losses, if you are close to the mode, there is some stability properties that are still not clear, but it helps to remain close. So that even if you have losses, if you inject energy, you're going to enter like any hysteresis around the mode. While for general isolated trajectory, you can say that.
No more questions.